There is this really fascinating paradox in the world of technology. We go out and we buy or download these incredibly sophisticated enterprise-grade tools, software that literally powers banks, government agencies, massive data platforms, and we assume, almost by default, that because they are professional tools, they're secure right out of the box.
Yeah, it's that shiny box syndrome. It looks sturdy. Maybe it has a huge reputation, so you just assume the lock is already engaged and you don't even check the door.
Exactly. But today we are pulling apart one of the biggest shiny boxes in the entire industry, which is PostgreSQL. I mean, it's the standard for open source databases. If you are building an app today, you are probably using Postgres. But the source material we're diving into today, a hardening guide from SOCFortress, which is aligned with the CIS benchmark,
Sure.
it basically shatters that illusion immediately.
It really does.
It flat out says, no, it is not secure out of the box. In fact, those default settings are often just a welcome mat for attackers.
It sounds alarming when you phrase it that way, but it's actually a very predictable conflict of interest. Think about the developers building PostgreSQL. What's their main incentive?
Getting people to actually use it.
Right. They want you to have a completely friction-free onboarding experience. They want you to run an install command and have a working database in 5 minutes. But security is friction. Security means barriers and passwords and access control lists. So naturally, the defaults are always going to prioritize usability over locking things down.
The happy path for the developer turns out to be the easy path for the hacker.
Precisely. So our mission for this deep dive is to look at this guide and figure out how to put that friction back in where it belongs. We're moving from easy to use to hard to break.
And what I really appreciate about this specific SOFortress material is that it's not just academic theory. It's built on actual observations from security operations centers. So these aren't just rules made up in a vacuum. These are rules written because someone, somewhere, got breached, and the SOC team had to say, hey, they got in because this specific setting was left on trust.
Yeah, this is what we call blood on the tracks advice.
Yeah.
Someone got compromised, so a rule was written to stop it from happening to the next person.
Okay, so here is the roadmap for our deep dive today. We are going to secure a PostgreSQL instance from the ground up for you. We will start with the foundation, so the operating system and the installation. Then we'll move to the front door, which is authentication. Then we go inside the house to look at authorization and permissions. And finally, we'll check the surveillance system, meaning logging and monitoring.
It's a full architectural review because, honestly, you can't secure the data if the foundation it sits on is rotten.
So let's start right at the bottom. The foundation. The guide opens with a pretty stern warning about supply chain risk. Now, usually, I have to admit, when I install software, I just search for a tutorial and copy-paste whatever apt-get or yum install command is right there on the screen. I am definitely not inspecting the URL.
Which is exactly how you end up introducing a compromised binary into your environment before you've even done anything. The guide is incredibly strict on this point. You absolutely have to trust your source.
Right.
If you are grabbing a PostgreSQL package from some random third-party repository just because it promises a faster install or maybe it has some cool plugin preloaded, you have no idea who actually built that package.
It could have a backdoor hard-coded right into it, or even just be an outdated version with a bunch of known CVEs.
Exactly. You want to stick strictly to the official PostgreSQL repositories or the signed packages from your OS vendor like Red Hat or Debian. Those are vetted. And there's another nuance here that a lot of teams miss, which is version pinning.
Version pinning, you mean stopping the software from updating automatically?
Not stopping it forever, no, but controlling exactly when it updates. If you just let your package manager automatically update Postgres every single time a new minor version drops, you run a huge risk of configuration drift.
Because things change under the hood?
Right. Maybe a default setting changes in version 15.2 that totally breaks your carefully planned security model, or a new feature gets introduced that opens a port you weren't monitoring.
So for the listener, you really wanted to explicitly state in your configuration, we are running this specific version, and we will manually review the release notes before we pull the lever to move to the next one.
You have to be the one pulling the lever, not an automated cron job.
Okay, so we have our clean binary from a trusted source. We install it. Now the guide starts talking about the blast radius, which sounds a bit dramatic for a database.
It's dramatic because the consequences of getting it wrong are catastrophic. Think about this. If an attacker finds a 0-day vulnerability in the PostgreSQL code itself, maybe the buffer overflow, and they manage to execute code on your server, the first question is, who are they executing that code as?
Ah, So if I installed it lazily and just ran the service as root?
Then they are root. The game is entirely over. They don't just have access to your database tables, they own the operating system. They can wipe the drive, they can pivot and jump to other servers on the network, they can install a rootkit.
That is terrifying.
It is, and that is exactly why the CIS benchmark is absolutely adamant about this.
Mhm.
You must run PostgreSQL as a dedicated, non-privileged user. Usually you just name it Postgres.
So if they break out of the actual database application, they find themselves trapped in a dummy user account that literally cannot do anything else on the server.
Exactly. It's basic containment. You are limiting the blast radius to just the database service itself, which hopefully saves the rest of your infrastructure. And by the way, that containment extends to the physical files on the disk, too.
File permissions?
Yes. You would be shocked how often incident responders find the actual data directory, the literal folder on the hard drive where the credit card numbers are stored,
Mhm.
just left world readable.
And world readable in Linux just means that any user account on that entire system can read those files. So if a hacker gets a low-level foothold on the web server account, they can just browse right over to the database folder and copy the files.
Right, they don't even need to log into the database. They just steal the raw files. So the guide mandates a strict permission setting of 700 on the data directory.
Let's decode that 700 for a second for anyone who isn't a Linux admin.
Sure. In Linux permissions, the first number represents the owner of the file, the second is the group, and the third is everyone else. So that 7 for the owner means read, write, and execute. Full control.
And the zeros.
0 for the group, and the 0 for everyone else means absolute access denied.
So even if I am a valid user logged into that Linux server, if I try to change directories into the Postgres data folder, the OS is just going to bounce me with a permission denied error.
Correct. You are essentially building a vault within the server, and only that specific Postgres user holds the combination.
Okay, so our foundation is poured and set. Now we approach the front door, authentication. And this is where the SOCFortress guide flags a critical severity misconfiguration. It's called the trust authentication method.
Ah, the trust trap. This one is notorious. It is actually the default in a lot of quick start distributions because it makes local development so frictionless, but it is effectively a policy of leaving the front door wide open.
What does that actual configuration line look like? Just so you know what to hunt for in your own config files.
You are going to look in a file called pughba.com. HBA stands for host-based authentication. And you will see a line in there that looks something like this.
Yeah.
Host all 127 by 0.132 trust.
Okay, let's parse that out. The word host means it's a network connection. All means it applies to all databases and all users. The IP 127.0.9 is the local machine loopback. And trust, well, that sounds nice, but I'm guessing it's really bad here.
It's way too friendly. Setting it to trust tells Postgres, look, if the connection is coming from this specific IP address, do not even ask for a password. Just let them in as whoever they claim to be.
Wait, really? So if I'm an attacker and I have somehow managed to compromise the front-end web server that happens to be running on that same machine, and I just open a terminal and type PSKOU PostgreSQL.
You are instantly the database administrator. No password required, no hash to crack. You didn't hack the database. The door was just unlocked because the database implicitly trusts the local machine.
That is wild because web servers get compromised all the time through totally unrelated vulnerabilities. You definitely don't want that to automatically equal a total database compromise. Lateral movement should be difficult.
Exactly. You want fire breaks. This is why you must change that authentication method. You need to switch it to SCRAM-SHA-256.
Let's talk about that acronym, SCRAM-SHA-256. I know MD5 used to be the old standard for passwords. Why is the guide saying MD5 is completely dead?
Because MD5 is fast. It was designed to be fast, which is a disaster for security today. Modern graphics cards can calculate billions of MD5 hashes per second. Billions. So if an attacker manages to steal your database password file, they can load those MD5 hashes into a cracking rig and brute force the plain text passwords in minutes or hours. It offers virtually zero protection against offline cracking.
So we need an algorithm that is intentionally slower and much more complex.
Right. And that's where SCRAM comes in. It stands for Salted Challenge Response Authentication Mechanism. It solves two massive problems. First, the SHA-256 hashing is cryptographically much stronger. But second, it completely changes the actual login handshake.
How so?
With older basic authentication, the client often just sends the password hash directly across the network wire. But with SCRAM, the server and the client play a complex mathematical game. They exchange cryptographic data back and forth to prove they both know the password, without ever actually transmitting the password or the hash across the network in a way that can be stolen.
Oh, so it stops replay attacks. An attacker can't just sit on the network, record my login traffic, and then play it back later to get access.
Exactly. It's vastly superior. But there is a huge operational gotcha in the guide that you have to be careful with here. You cannot just open your config file, change the word to scramshaw256, and restart the database server.
Why not? Does it break?
It totally locks everyone out
Right.
because all the passwords currently stored in your database are still hashed with MD5. Postgres can't magically upgrade those hashes to Scram because it doesn't know what the original plain text passwords are.
Oh, wow. So you have to change the configuration, and then literally every single user and service account has to log in and reset their password so the system can generate the new hash.
Yes, it is a massive operational headache. You have to coordinate with your entire engineering team.
Yeah.
Everyone needs to rotate their credentials this Friday night at midnight. But it's absolutely necessary pain to secure the system.
Well, speaking of things traveling across the network wire, the guide gets very strict about TLS transport layer security, which most people just think of as SSL.
If you are not enforcing SSL, your database traffic is just flying around in clear text. If I am sitting on the same network segment as you, maybe doing packet sniffing, I can literally read your SQL queries. I can see you send select from users, and I can read the actual user data coming right back in the packet capture.
So we just go into the config and set SSL on. Is it really that simple?
Simple to type into a text file, but much harder to actually implement in production. And the reason is certificates. If you try to cheat and just use a self-signed certificate, your application backend, whether it's Java, Python, Node, is going to throw a massive error saying it doesn't trust the issuer of the certificate.
So you are forced to manage a proper public key infrastructure, a PKI, or manually distribute that certificate out to all your client machines.
Yeah. People forget that security is often just logistics in disguise. But if you skip TLS, you are essentially broadcasting your sensitive data to anyone listening on the local network.
Okay, so we've authenticated. We are legally inside the database now. Next up is authorization. Who has the keys to which specific rooms inside the house? The guide spends a ton of time warning about the superuser.
The superuser role, which is usually that Postgres account we talked about, is basically God mode. It bypasses every single check and balance in the system. And the guide attacks a very, very common lazy developer habit here, which is connecting your web application to the database using the superuser account.
I have seen this happen 100 times. A developer is trying to get a new feature working, they keep getting permission denied errors, and finally they just say, you know what, just give the app admin rights, it works now, we will fix the permissions later.
And later never ever comes. Here is why that is so catastrophic. Postgres has a brilliant feature called row-level security, or RLS. It lets you write policies that say, user A can only see rows in this table that explicitly belong to user A. It is the gold standard for building secure multi-tenant applications.
But if you connect as the superuser,
the superuser ignores row-level security entirely. It bypasses it. So if your application connects as superuser and a hacker finds a simple SQL injection vulnerability in your web form, they can suddenly read every single row and every single table, regardless of how carefully you crafted those RLS policies. The security checks simply do not execute.
So the rule from the CIS benchmark is absolute. Applications never, ever connect as the superuser.
Never. You have to implement the principle of least privilege.
the guide breaks this down into a really clear hierarchy. It talks about login roles, privilege roles, and ownership roles. Can you sketch out how that works in practice?
Sure. You are essentially separating the concerns. Your login roles are the actual identities, like a user or report user. These roles are allowed to connect to the database. Then you have ownership roles. These roles own the tables and the schemas, but crucially, they are not allowed to log in at all. And finally, privilege roles are basically groups. So you grant a read-only access privilege role to your reporting user.
So if that reporting user account gets hacked, the attacker can't drop tables or delete data because that account physically doesn't have the right privilege. They are completely boxed in by the architecture.
Exactly. And more importantly, they definitely shouldn't be able to create new users, which brings us to the concept of persistence.
Right, the spy movie stuff. How does an attacker maintain their foothold in the system once they get in?
In Postgres, there's a specific permission flag called role creator role. If an account has this set to true, it can spawn other users.
I see exactly where this is going.
Yeah.
I compromise a low-level application account that accidentally has this flag enabled. I use it to secretly create a brand new account. Maybe I name it something innocent like System Backup Service. I give that new account super user rights, and then I just log out.
Yep. And then even if the security team detects the breach and forces a password reset on the originally hacked account, it doesn't matter. You still have your back door. You have your fake system backup service user just sitting there waiting for you.
So how do you check for this? We need to actively audit the progress table.
You literally just run a query. Select a role name from tcrols, where role creator role true. If that query returns anything other than your tightly controlled main database administrator accounts, you have a massive security incident on your hands.
Let's pivot to network exposure. We already talked about authentication, but this is about where the database is even listening for connections in the first place.
Yeah, by default, or at least in a lot of quick start guides you find online, you are told to set your listen addresses to an asterisk, or 0.00.0. That essentially tells the server, listen for connections on every single network interface you have.
Public IP, private IP, VPN tunnel, everything.
Right. And if that server happens to have a public IP address attached to it and you bind to 0.0.0.0, your database port, which is 5432 on MIC, is now directly facing the entire public internet.
Which means Shodan is going to find it.
Shodan will find it in minutes. For those who don't know, Shodan is a search engine for internet-connected devices. And there are automated botnets out there scanning the entire IPv4 address space for port 5432247. They will find you, and they will start brute forcing you immediately.
So the fix is to bind the listen addresses only to 127.0.0.1 if the app is on the same machine, or to the very specific private IP address of your internal virtual private cloud.
The database should essentially be a hermit. It should live in a dark room. It should only speak to the application server and nothing else. And this is exactly where network firewalls come into play. Even if the database is technically listening, your firewall rules should instantly drop any packets arriving at port 5432 unless they originate from the exact known IP address of your app server.
Defense in depth. Now, suppose all of those walls fail. The firewall is bypassed, the attacker slips in. How do we even know it happened? We need to talk about the black box, the logging and auditing system.
Logging is really the unsexy hero of the security world. And the SOCFortress guide makes a very strong point here. The default logging configuration in Postgres is optimized for performance. It is not optimized for forensics.
Meaning it just doesn't log enough detail?
It barely logs anything useful for an incident response team out of the box. The guide gives us a clear list of must-haves. The first one is turning on log connections and log disconnections.
That seems pretty basic, just recording who entered the database and who left.
It is basic, but it is absolutely vital for building a timeline during a breach. Next, and this is crucial, you need to set log statement to DDL.
DDL. That stands for data definition language. Why specifically DDL?
Because DDL commands are the ones that actually change the structure of your database. Things like create table, drop table, alter user. If you think about a normal running web application like a shopping cart, does that app ever need to drop a table in the middle of a Tuesday?
No, of course not. It just reads product inventory and writes new orders. It definitely isn't redesigning the database schema on the fly.
Exactly. So if you ever see a DDL command pop up in your production logs, it is a massive, screaming red flag. It means either a developer is doing something incredibly reckless in production, or an attacker is actively trying to delete evidence or grant themselves new permissions.
What about logging the actual data queries, like every select statement?
That is a classic operational trap. If you tell Postgres to log every single select statement, two catastrophic things will happen very quickly. Number one, you will fill up your entire hard drive with log text in a matter of hours.
And number two,
You will crush the database performance because the server is suddenly spending half its CPU cycles writing text to a log file instead of serving data to your users.
so you have to be highly selective. You log the structure changes, you log the errors, and you definitely log the failed logins.
Yes. A brute force password attack just looks like 5,000 login failed events clustered into a single minute. If you aren't logging failed attempts, you will literally never know someone is trying to kick the door in.
Yeah.
You have to capture that signal.
We are entering the final layer of the guide now, defense in depth. This covers the worst-case scenarios where your digital walls are bypassed, or even where physical security is breached. Encryption at rest.
This is the classic data center heist scenario. If I manage to walk into your server facility, physically pull the hard drive out of your database server, and take it home, can
Yeah,
have
exactly.
data
Without
gone.
encryption, yeah. It's just flat files on a disk.
Exactly. So the guide heavily recommends full disk encryption at the OS level, using tools like LUKS on Linux. But there is another really sneaky attack vector inside the database that we need to touch on, which is extensions.
I honestly love Postgres extensions. Things like PostGIS for geospatial data or PGStat statements for performance monitoring. They make the database so much more capable.
They are incredibly powerful.
Yeah.
But from a strict security perspective, installing an extension is basically giving someone a way to run arbitrary code directly inside the database process memory.
And if the database engine is running as that Postgres user we talked about,
Then the extension code executes with all of those Postgres user privileges. There are explicitly malicious extensions out there, obviously, but attackers can also abuse perfectly legitimate extensions like pgcrypto or Python to break out of the database and execute operating system commands.
so the mitigation there is to rigorously restrict the create extension privilege.
Rigorously. Only your true, heavily audited super user accounts should ever be allowed to load new compiled code into the database engine.
Finally, we have to talk about the ultimate safety net, backups. The guide mentions two specific acronyms, RPO and RTO.
Recovery point objective and recovery time objective. They sound like fancy MBA jargon, but they just answer two brutally simple questions. How much data can this business afford to lose? And how long can we afford for the system to be down?
And the security angle here isn't just making sure you take the backup, it's making sure you secure the backup.
You wouldn't believe how many companies spend millions of dollars on firewalls and database security, and then they just run a nightly script that dumps their entire production database into an unencrypted text file on a shared network drive.
Oh,
You just took all the gold out of Fort Knox and left it in a cardboard box on the sidewalk. Your backups absolutely must be encrypted. They must be stored off-host. And this is probably the most painful lesson in the entire IT industry. They must be tested.
Schrodinger's backup.
Yes. Until you have actually successfully restored it to a different server, your backup does not exist. It is merely a hopeful hypothesis.
I feel like every single system administrator has a deep personal scar from a backup that the system verified as successful but totally failed to restore when the server actually caught fire.
It is an industry rite of passage. Don't let it happen to you. Test your restores quarterly at a minimum.
So looking back at this entire roadmap we just walked through, from the SOCFortress guide, we have hardened the operating system, we locked down the network exposure, we upgraded the authentication to Scram, we compartmentalized the authorization rules, and we finally turned the lights on with comprehensive logging.
We took a very soft, user-friendly default installation and turned it into a heavily hardened target.
But the expert in me knows this is not just a one-and-done project.
And that is exactly the final and maybe the most important takeaway from this entire discussion. The concept of configuration drift.
Drift, like a boat slowly drifting off course over time.
Exactly. It's entropy. It's disorder. You can follow this guide perfectly, set all these configs up on day one, and get your security gold star. But 6 months later, it's 3.0 a.m., and a developer is desperately trying to debug a connection issue. They are exhausted. They can't get the application to connect to the database. So they temporarily change that pghpa.conf file back to trust, just to quote-unquote test something. They fix the bug, the app comes up, and they go to sleep.
And they completely forget to change it back to Scramshaw 256 the next morning.
And just like that, silently, your hardened fortress has the back door propped wide open again. This is exactly why the concept of infrastructure as code and automated auditing are so critical. You absolutely cannot rely on manual security checks. You need an automated script that runs every single night, compares your current live settings against your CIS baseline, and actively alerts the team if something has drifted.
Because security isn't a state you achieve and then forget about. It's a continuous process that you have to actively maintain.
Perfectly put. The threat landscape is constantly changing, and human error means your configurations will try to change too. You have to be eternally vigilant.
Well, this has been an incredible deep dive. I am definitely going to go check my own pghba.conf file the minute we finish here.
It is always worth a double check.
Thank you for guiding us through the depths of PostgreSQL hardening today.
My pleasure.
And to you listening, stay secure out there, keep your package versions pinned, watch out for drift, and we will catch you in the next deep dive.